Okay, so we are very excited then to get started. We have an excellent talk this morning from Dr. Eddie Schoute, previously of Los Alamos National Laboratory, but most recently of IBM. He will be giving us a brief, let me read the title real quick, a brief tutorial on quantum error correction. Eddie, turn it over to you.
Hello, I hope you all can hear me, even though I'm wearing a mask. I was kind of feeling a little off this morning, so I thought I'd protect you all from whatever I'm carrying with me. Um, so I'm here to give you a brief tutorial on quantum error correction, and I thought this would be quite a diverse crowd, so I don't want to go too fast. If you're familiar with error correction, great, prod me, but don't expect any, very new results to be in this talk. So first, let's start with classical error correction because that's easier to reason about. Maybe the simplest way to protect your data in a classical setting is just by repeating it. So if we want to send a bit 0, then we can encode it in the string 000. Or if we want to send a bit 1, we can encode it in the string 111. And why does that help? It's because then we can detect 1 or 2 errors, as in the errors being bit flips. There are, of course, many other kinds of errors in the world, but let's stay focused in this talk. And if we take a little majority vote, then we can actually correct at most 1 error if we have repetition code, 3 bits. So now if we have IID bit flips, so independent bit flips occurring with probability P, then we now, after encoding this in the 3-bit repetition code, we have an order P squared error probability. So we have suppressed our error, asymptotically from linear to quadratic, and P here is going to be some small number, 10 to the minus 3 or something like that. So now we have 10 to the minus 6 error probability, much better. So now let's see how we can use this to send a longer bit string. So let's say we have the bit string 001 and we want to send it over the network where with probability P, IID bit flips happen. So if we encode the bit string 001 using our code, then the first bit will be encoded as 000, second bit 00011. I hope it's clear so far, and feel free to interrupt me. I hear we have 30 minutes for questions, so there's quite a bit of time. Now, if in our error channel, so the network, your router screws up or something, or a cosmic ray hits your memory or something like that, some of the bits get flipped. Okay, so if in our error channel we have a few bit flips, in this case I picked them to be 1, at most 1 per code block, so we can actually correct the errors. Indeed, when we do the decoding by doing a majority vote in each block, then we have successfully transmitted our logical information over the network or over the error channel if only 1 or less errors occurred in each block. So now you might wonder, can I scale this up, and what will happen when I scale this up? And usually we look at this by considering code thresholds, and they are commonly computed numerically, and they will tell us when it's worth it to use a code. So for example, for the repetition code, I took this picture from Delphos's tutorial. I mean, it's easy to generate, but it's easier to take from somebody else's talk. So this is a linear plot. I mean, usually you would see it in a log-log plot. But if your bit flip probability P is below a half, I don't know, I don't want to use the laser pointer too much because it's not on all the screens. So here at halfway through, we have the bit flip probability P. And if our error probability is larger than 0.5, then we see that increasing the code distance, so more and more bits per logical bit, we actually get worse, right? Because now we're increasing the likelihood that some error occurs. However, if the bit flip probability is less than 0.5, then we're actually suppressing the likelihood that the bit flip occurs. And another way to see that is that if, for d equals 3 is the code that we saw before, But if we have d equals 5 or 7 or 9, so that means we take one bit and encode it in 5 bits, right? So 0, 0, 0, 0, 0, or something like that, or however many bits you want, then we actually suppress the error probability. Okay, so one big thing to note in the quantum world, there are not only bit flip errors, there are also phase errors. And our simple repetition code cannot detect the Z errors, right? Because a phase occurs and we have no knowledge of that happening. I mean, I guess we were in the classical world, so there are no phase errors, but in the quantum world, we need to protect our code words from the phase errors. So it actually has a 0 threshold for quantum error channels, because it cannot even detect one error, no matter how many bits we use to encode our logical information. And in this particular example, so we have seen the repetition code, which doesn't have a threshold, but it is still, useful, right? If you know your device has overwhelming likelihood of having bit flip errors, or overwhelming likelihood of having phase errors, then maybe a repetition code can actually help, right? If you do the appropriate Hadamards. Yeah, question?
What exactly is the threshold?
A threshold. Yeah, so the threshold, maybe I should have said it more explicitly, but the threshold here is the intersection of all the curves here. So below the threshold, which is 0.5 here, we can increase our code distance arbitrarily and suppress the error arbitrarily, right? I mean, up to size limits, right? But if we wanted to have an error epsilon, you give me the epsilon, then I give you the code distance. It might be huge, but I can achieve any epsilon you want, as long as our IID errors occur and it's below this threshold. Yeah, good question. Any other questions? Also, is it common to repeat the question? Because I don't know if everybody, yeah, I see. Okay, yeah. Or do I have to run with a microphone? Okay. All right, so let's put this on a more formal footing and introduce what are known as linear codes. So when we have code word C, code words, so C is a set of bit strings that are sort of valid code words. So in our example, it was 0, 0, 0 and 1, 1, 1. Then the set C is a linear code. If for any X and Y and C, we can add them in F2 and still get a code word. So let's look at an example. So our repetition code has two code words, 0, 0, 0 for the 0 logical bit, and 1, 1, 1 for the 1 logical bit. And we can verify that C is linear by considering all linear combinations. Well, adding any of the two code words, right? I said linear combination, but I shouldn't have. So for example, if we add 1, 1, 1 to 1, 1, 1, then we get 0, 0, 0, because in F2 or Z2, 1 adding to 1 becomes 0, right? We're doing sort of vector addition in a finite field. So now, since the repetition code is linear, we can actually consider some set of logical bits as a basis, and construct code words through what is known as the generator matrix. So for the repetition code, the generator matrix is just 1, 1, 1. And if we have our logical information, then we can encode it in our code by multiplying it with this matrix. So in particular here on the left, we are multiplying the 0 vector, which stands for the 0 logical information, with the generator matrix 1, 1, 1, and that means we get 0, 0, 0. Because 0 times 1 is 0, for every entry. And similarly, for 1 times G, we get 1, 1, 1. And this generalizes to any linear code. I mean, that's kind of why they're called linear codes, right? We can use linear algebra to reason about the linear codes. So I hope it's been clear so far. Okay. So just to reiterate, we have now encoded k equals 1, a logical bit, by using n equals 3 physical bits. And I'm saying n and k because later on, you know, these parameters will be used. So since we so since there are only 2 code words, we have a generator matrix that has only rank 1. And then, you know, from basic linear algebra, you know there is an orthogonal space, right? We can look at the space of bit strings that are orthogonal to our generator matrix rows, and in particular, these are spanned by what we call a parity check matrix. So it's just the orthogonal subspace. And note that since it's a subspace, we can also consider linear combinations of these basis vectors, right? So another orthogonal or entry in the parity check matrix could be 1, 1, 0 plus 0, 1, 1, right? So 1, 0, 1 could also be a valid entry in the parity check matrix. So now we have the parity check matrix, so it's easy to check if it's a code word, because if a vector is orthogonal to the subspace in the parity check matrix, then it's a valid code word. So we just multiply the parity check matrix H with our vector X that we want to check, and it will tell us, is it a valid code word or not? So if we take H and we multiply it with the all ones vector, then we get 0, so it's a valid code word. But if we take it with some vector that has, you know, an error, then we get 1 because it's in the orthogonal subspace. Okay, so we can sort of summarize the properties of our linear codes by using the NKD notation. N here stands for the number of physical bits that we use to encode our logical information. K here is the number of logical bits that are encoded in one, you know, code block, in one code word. So in particular, you know, for the repetition code, we have k equals 1 because we're encoding 1 logical bit. And finally, D stands for the code distance. And this is a bit trickier to compute. But what it means is that if we have any 2 code words, then the distance between them, so in the Hamming distance, is at least D. So we need to flip D bits to go from one code word to the next. And this directly relates to how many errors are required for you to confuse 2 encoded words, because if there are D errors, then that could flip you from one code word to the other. And, you know, relatedly, the number of errors that you can correct is D minus 1 over 2. Right? Yeah. Oh yeah. Okay. So we saw earlier the error channel, right? Maybe all the way at the beginning. So if we encode our logical bit, actually, let me repeat the question so everybody can hear. What do you mean by the bit flips, right? Well, what does it mean, D bit flips? So if we encode our logical bit using 3 physical bits, and an error occurs, as in a bit flip error, because we're in the classical world, then it flips 0 to 1, right? And if 2 errors occur, then it flips 2 bits from 0 to 1, or it could flip the 1 back to 0, but then, you know, you're good. So it kind of corrected itself. So then if D errors occur, right, in this case, D equals 3, you could go from 0, 0, 0 all the way to 1, 1, 1, and you wouldn't know that anything even happened, right? At the receiver side, you would see 1, 1, 1 and decode it as 1, right? That's the code distance. So the question is, it doesn't matter where the errors occur. It does matter. Like I said, if two errors occur on the same bit, it would flip it back to 0, for example. And some codes, they're more sensitive to a particular string of errors, or less sensitive to other strings of errors. I have an example way at the end for the service code, but see if we get there. Yeah. Yeah, another question? Oh, yeah. Yeah, okay, good question. That's because we are working in a finite field of size 2, right? So if you add 1 to 1, you get 0. Yeah, and if you multiply 1 with 1, you get 1, 0 with 1, 0. These things are, yeah. Another question? If it's unprotected? Oh. Let's see. So that's a bit where so if the bit is completely protected, what is D, right? Is that the question? So for just a physical bit, let's say you send the bit 0 by encoding it in just 0, right? You don't do anything. Then the code distance is just 1, right? One bit flip would flip that 1 bit. So maybe you should clarify what you mean by completely protected. Yeah, so that's the definition that I showed you. It's not basically you enumerate through all the code words, right? Which there are 2 to the k, and then you compute the distance between all the code words, and that gives you a lower bound for D. So in our repetition code, there's only 2 code words. So we only need to subtract 111 from 000, and then the Hamming distance is 3. So the code distance is 3. Another question?
So if you had something more sophisticated and you had a higher ranked generator matrix, would that representation be unique, or just as long as it kind of like expands the code space?
Yeah, that's right. Is the generator matrix unique? It's not, because the subspace can be encoded in basis vectors in many ways, right? Including linear combinations. And there's a standard form. You could do row elimination, right, to kind of bring it into a standard form. But all of them are valid generator matrices. Yeah, that's a good question too. Any other questions? Oh, yeah. Yeah, in the classical case, can there even be phase errors? No. Because it's classical, I guess. Yeah. Yeah. Maybe I confused you with that bit of information. It's just to note that if you were to use this code in the quantum setting, it wouldn't work for all errors that we encounter, right? In the quantum. Because if phase gets flipped, then we wouldn't notice at all. So you can't just take ket 0 and then encode it as ket 000 and then expect to have code distance 3, right? Because one phase flip you wouldn't catch. I mean, in a superposition, right? If it's a global phase, then we don't care. Okay, maybe last question. How did we compute this N1N? How did we compute it? So N and K are easy to compute, right? The distance you can compute by doing that subtraction and the Hamming distance for all pairs of code words. Or you can prove a theorem, right, analytically. Okay, so let me continue. I have many more examples, so maybe it will elucidate. So recall that if we have the parity check matrix of the repetition code, and it could look like this. Now in the quantum setting, we want to check for bit flip errors and phase flip errors. And how do we do that in the quantum setting? Well, we can check for bit flips using a Z-type measurement. And why is that? It's because Z anti-commutes with X. Okay, so if we had an X error occur somewhere before our measurement, and then we have a Z-type measurement, then if we commute it through X, then the eigenvalue gets flipped. Right? So we can kind of see if we measure a Z parity that something has happened. So if we write our repetition code, our classical repetition code as the following matrix, where we just replace our ones with Z, then we have a quantum repetition code that protects against bit flip errors. And how would we implement this particular parity check matrix? So we can measure this Z1, Z2 parity check measurement by simply using a C0 into an ancilla qubit and then measuring that qubit. So what this ancilla here does, it's going to check that the parity of the first 2 bits is the same. And if you recall the code words 000, 111, the parity is always the same between any 2 bits, right? So we can also check the second and third bit, see if the parity is the same. And we can check the first and third bit and see the parity is the same, etc. So now if we want to correct errors, we just have some classical computer hanging on our device that processes these syndrome measurements and then picks the right X-type bit flip to apply to our code, right? So if we have one X error occur on the first qubit, for example, only our first ancilla Z1, Z2 would be flipped, right? We would get a 1 outcome in this measurement. So then our classical computer can be like, hey, Z1, Z2 was flipped, but Z2, Z3 was not. So therefore, there must have been an error on X1, like on the first qubit, and we can correct it. I hope that's somewhat clear. Oh, yeah. Yeah, I haven't defined the notation. So let's read this parity matrix, right, in columns. So this is the first qubit, second qubit, third qubit. So if you have a Z in this column, so when we look at one row, that's one stabilizer. That's how it's called. Then we apply a Z stabilizer on the first qubit, and a Z stabilizer on the second qubit, and nothing on the third qubit, so identity. And we get a Z1, Z2 stabilizer. Similarly, for the second row, we get a Z2, Z3 stabilizer. Yeah, so these are not going to be code words. They are in the parity check matrix. So rather, they are they tell you measurements to do that tell you when you're not in a code word, right? It's like your bit. If you recall the parity check matrix, if you multiply it with the bit string, you get 1 if it's not a code word. Yeah. So this will check each of the basis vectors in your parity check matrix one at a time, right? It will check if whether it is orthogonal to 1, 1, 0, and then it will check if it's orthogonal to 0, 1, or Z1, Z2, or Z2, Z3. So yeah, so the depth in this particular circuit would grow with the number of stabilizers. However, the stabilizers must always commute. Therefore, you could measure them simultaneously, right? In some smart way. There's some very refined attention you need to pay with the order of measurements, but we're not going to go into it. You can, for example, take these C knots, they're all controlling only, right? So you could do it simultaneously, right? Theoretically. Or, you know, as long as the targets are separated. Yeah. Sorry, another question?
So we are kind of holding like the orthogonal, like the orthogonal with the like the polar
Mhm. Yeah, that's a good question. So the question is, why are we not checking the generator matrix? Why aren't we checking the code space? And that is because if we measure the code space, then we're measuring our logical information. So we would be destroying sort of the quantum superposition that we have prepared. Let's see. No, wouldn't generalize because you don't have a superposition. Yeah, another question. Yeah, so what is this process syndrome? It is purposefully a black box. It's a whole subfield, you know, of research in error correction. It's basically what is known as a decoder, right? So it takes in classical bits of information from your error correcting code, and then tells your quantum computer what corrections to apply to your data to fix the errors. Is it like an oracle? No, it has a defined implementation. And the performance of your error correcting code depends also on this implementation. So if you think about, like, say, some recent papers, these days, they will pick a decoder that scales in exponentially in time because it gives them the best performance. But if you were to scale this, you know, arbitrarily large, then it wouldn't work anymore, for example. Yeah. Any other questions? Yeah.
So for the last gate, is this a universal notation or?
Yeah, the last gate, maybe I was lazy, but it's just controlling on what the classical computer outputs. We are applying 1 bit flip somewhere or 2 bit flips or something like that. Yeah. Another question?
Basically, what is detecting that 1, 0 happened, then you apply X1. Like, how do you do that? Like, you basically, my question is like, you get like your classical bits, and then you apply like a control symbol, it's a classical. So what do you actually do? Like, once you show up the result, you know that it's incorrect. Put it in your output, or you actually do like quantum.
Right. So what do you actually do? What does it mean to have these bit flips at the end of the process? So sort of in the simplest setting of error correction, your classical computer, you do the measurement. It goes through a wire to the classical computer. It does some number crunching. Then through another wire or some control mechanism, it then tells the quantum computer, hey, apply X1 to this qubit. What do you mean by final state here? Is that the end of this circuit, or is it? Yes. Well, you would need to know the syndrome information to compute those X gates. Yeah. However, in practice, since we're only doing Pauli corrections, and you might know that Pauli's commutes can be commuted through Clifford gates, you can kind of defer your correction operation. And why is that? It's because this wire here, right, measuring slow, depending on which system you're considering, then the classical computer has to process it, which is slow, and then it has to send it back to the quantum computer, and that's slow too. So if you were to do this, you know, actually in a quantum device, you would be slowing down your computation like massively. Right? This would kill, you know, probably would kill like a superconducting architecture because they're working on such small time scales. right? If you're thinking about longer time scales, then you might have time to do more thinking. Yeah. Any other questions? Okay, great. Thanks for the questions. Let's keep going. Okay, time to construct our first quantum error correcting code. I pulled out a more complicated classical code, which is called the Hamming code. And Hamming code uses 7 physical bits to encode 4 logical. Wait, maybe 3 and 4 are flipped. So, but to encode 3 logical bits. Am I missing a row or something? Okay, I'm gonna fudge that. So it's a 743 code or a 734 code, and it has the following stabilizers. So now I'm just going to copy this matrix and replace all z's with x's. And ta-da, we have the Steam code. So this allows us to correct any x or z error or x times z error, which is proportional to y, except for a phase. And this is actually a 713 code. But now I use double brackets to say it's a quantum. It's a quantum code. So, and we can correct three errors. Well, no, we can correct 1 quantum error, and we can detect 2. Say x or z or xz errors. Right. I haven't proved that to you, so let's dive into that. But let me note that a CSS code is a code that consists of solely z and of solely x stabilizers, right? So this is a CSS code because every row is just z's or it's just x's. So now if you see CSS code, you know kind of what it means. You don't know what it implies, but yeah. Yeah. I think it's named after some folks. It's Calderbank, Steen, Short, or something. I think. I'm not good with names. Yeah, in the back. I'm not sure what you mean by powers of Z and X. Oh, I see. I don't know if it's defined on qubits or higher dimensional systems. It might exist some literature, but we're working in the qubit setting. Yeah. Question?
Maybe it's how do we know that now going from Z to X, go from 4 bits to
Yeah, so why are we encoding less information? Is the question, right? So maybe one way to see it, I will talk more about it in the next slide, is that now our parity check matrix, right? If we think back about the classical case, has rank 6 out of 7 dimensions, right? Because we have 6 rows of these stabilizers. So there's only 1 dimension left to encode our logical information, which is a qubit. It's that simple. It requires some theorems to prove that, to you, but you could read about it in the literature. Yeah. Another question?
like, can you show us like what the actual encoded qubit looks like?
I think I will talk about that in the next slide, the encoded qubit. Yeah, another question. How did we get 713 here? So how did we get 713? Well, 7 and 1 we can easily compute, right? Because we know we are encoding our information in 7 qubits, just from the width of this matrix. 1 is the result of having 7 qubits, but also having 6 stabilizers. So it's 7 minus 6 equals 1. So you have 1 logical qubit. I'll talk about that in the next slide. And finally, the code distance is a bit more complicated. you know, either you show theorem or you just enumerate 2 to the 7 code word or 2 to the 1 code words, right? And then you see, okay, I need three poly errors to flip from one to the other. Okay. Yeah, so to correct the errors, we would measure each of these stabilizers one by one, or you know, in parallel if you're being more fancy. And then if one of them flips, you will know that an error occurred. And then your decoder will magically, not magically, but you leave it to computer scientists to code up some program, and it will tell you, okay, I'm going to guess that this error occurred. That seems very likely to have occurred. Right? Yeah. Another question?
Yes, I still don't understand this going from 4 to 1.
Yeah.
Because it seems like replacing all z's with x's, that's just some global unitary rotation.
Mm.
And so I don't understand how like you're shrinking your code space.
Okay, so why can we replace our z's with x's? They're equivalent up to some unitary, right? So I guess the important fact here is that the stabilizers still commute, right? So if you take this string z, 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 z and x, 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 then these two strings commute, right? So if you look at the larger Hilbert space, then these two can be sort of, these two have a similar +1 eigenvalue, right? So that's sort of the stabilized code space. I will define it also in a later slide.
Also, it is always true. The code pieces, they change, like behind the code, this code.
It's not always true that we just replace these with x's and then get a quantum code. But in this particular case, it worked. Yeah, and it became famous. So, and it's easy to explain. Okay, maybe last question in the back left. Yeah, we need all the stabilizers to commute. So what, yeah. I will also, I'm gonna hold on the questions because I'm getting a lot of questions that I think I'm gonna answer in the next slide. So, you know, now we just put a big matrix, which are the, you know, put all the rows together. And these are the stabilizer generators of this 713 code. And they protect our information from these poly errors, as I've claimed. I haven't proven it to you. But maybe more importantly, do we even have room in our code to encode logical information, right? We had a lot of questions related to that, and yes, the answer is yes. Why? Because all the stabilizers commute. I mean, that's a requirement for the stabilizers. So indeed, there's a 2 to the 7 minus 6 dimensional subspace. That is the common +1 eigenstate of all the stabilizers, right? You can sort of simultaneously diagonalize all of them. You know, since 2 to the 1 is 2-dimensional, we have a qubit. So that's where the 1 comes from in 713. And the logical operations which act on this qubit, they must also commute with all the stabilizers. And in particular here, our logical operations, which I write bar z and bar x, are just the all z string and the all x string. Oh, I hope that helped clarify some of the questions. I'm going to peek in the next slide. But if you now still have questions about the logical information, then please shoot. Yeah, question.
And by Alamos,
Arbitrary unitaries. So the poly errors, they're a basis, right, for unitaries. You can write a unitary as a linear combination of polys. So your unitary will always, you can always decompose it. in terms of a number of poly errors. Now, if this, it doesn't mean that any one unitary you could correct, right? One unitary could have 7 bit flips in there, right? Like all X string. But an arbitrary unitary can be decomposed in some linear combination of poly errors. The dimension of that unitary will be always 2 to the 7. Sort of the non-trivial support, I don't know how to call it, might be more relevant. Like, let's say this unitary only touches 1 qubit, then yes, you could correct any unitary acting on only 1 qubit, right? Because we can correct any error, and this unitary can always be decomposed in like acting as X, Z, or Y, or identity, some linear combination of. And each of these we can deal by linearity. Yeah, so there are some results about what types of errors you can deal with. I'm not really going to talk much about it though. Yeah, but if you have random poly errors, then this is a fairly broad class of errors. It means it's 2 to the 1. Yeah, it's trivial. Oh, I'm just making it explicit. Yes, that's right. In the classical version, we had 4 logical bits, and here only. I hope I didn't flip. So I think I flipped the 4 and the 3 for this matrix. It's 734 code. I would need to double check. So it's actually 3 logical bits. Okay, let me look to the side. Yeah, you have a correction for me? Okay, yeah, so but sometimes K and D are switched. So which one are K, which is K, and which is D? Just to set the record straight. So while you look that up, let me see if there's any other questions. Yeah. Yeah, it's not obvious. The code distance is something you would have to compute. For small codes, you can do it exhaustively. You check all the code words, and then you see you can kind of compute, what errors could occur to flip one from the other. I think it's not trivial because the logical operators here seem to have this 7, right? But if you multiply these logical operators with some of the stabilizer generators, then the weight reduces. And those are also logical operations, right? So if I take ZZZ and multiply it with this all Z string, then I would still have a logical operation. I hope I'm saying this right. What is the smallest length of a stabilizer? Well, in this case, it's 4. Well, if that's what you mean. Okay, another question. Yeah, all the stabilizers must commute. Yeah, otherwise it's not stabilizer code by definition, right? It's so that we can measure all the stabilizers simultaneously, and the code space is sort of they're called stabilizers because they make this code space stable. Like if you have a code word in the code space, if you measure any stabilizer, it will be unchanged because it's a +1 eigenstate. So you can measure it as often as you want. Measure the first stabilizer 100 times, measure the second one 2 times. It won't change the code word. Okay, maybe one last question. Yeah. Yeah, so how did the logical qubits in this case, why did it go down from the classical code? It's because we added more stabilizers to our code. So recall that we are, from the classical case, recall that we are writing down the parity check matrix, but in a quantum setting, and each of these is telling us, oh, this is a bit string that is not in our code space, right? So we're kind of increasing the subspace dimension of words that are not code words, right? So sort of, yeah. Yeah, we're working on the orthogonal subspace here for the code from the code words, right? Yeah. Okay, I'm gonna pause on the questions for a second. How am I doing on time? Let's see, 9:50. Okay. Well, I don't want to eat your break, but I want to eat in the break, but no. Okay, so maybe one thing that confused me a little bit for when I was learning this is okay, well that's cool and all, but how do I what does logical zero mean in our code? And if we recall, all our stabilizers, they commute, and we have defined sort of the logical subspace to be the common +1 eigenspace of all the stabilizers. So all we need to do to construct a logical state is just take a random string. Here we take the all zero string and start projecting down into the +1 eigenspace. Just keep doing that. And if you're in the +1 eigenspace of all the stabilizers, you will have a code word by definition. And an easy choice, right, to begin with is the all zero string, because it is already in the +1 eigenspace of any Z stabilizer, right? So if we project down into the +1 eigenspace of Z stabilizers, the all zero string just stays the same. So now let's measure XXXX, right, which is the first stabilizer of our first X stabilizer of our Steam code, right? It's a Steam code. Then what happens? Well, we get a superposition, right? So one is the all zero string and the other is the all zero string, but we apply XXXX, right? And then there's a random phase. Luckily, we know what the phase is, so we can correct it by applying a 1 qubit Z operator. And more generally, you can sort of post-select on the A = 0 outcome, because there is such a correction you can apply, right? So that simplifies sort of the tracking I have to do. Well, actually, I'm not going to continue too much, but there's a homework question, so it will help you. So now you can check for yourself that the resulting state, is it still a +1 eigenstate of all the Z stabilizers, right? Because we applied some operation to it. And if we apply the remaining 2 X stabilizers, then we get us the logical zero state. And note that this will double the number of strings, right, in our superposition at every step. So I didn't write it out because you would get a whole bunch of stuff on the screen, but it wouldn't tell you much. And then we have our logical 1, which is just applying the logical bit flip to our logical zero state, right? Yeah, so I very briefly flashed what a logical bit flip is, and for this Steam code, it's just an all X string. So when we apply all X's, we go from the logical 0 to the logical 1. It's just like your regular polys, but you put a bar on top of it. Yeah. Okay. Maybe let's have some more pictures in here, because that's sort of the main innovation of surface codes. We've looked at matrices and stuff, but we all have we live in the 3-dimensional world. So if we can draw like a picture on a 2D space, then it will help us measure these stabilizers, right? Because if our stabilizers are all geometrically local, then we can actually build a device that measures those stabilizers efficiently. So I'm going to say that if I draw a yellow square, then I have a Z-type stabilizer. And if I draw a blue square, then I have an X-type stabilizer. Then a surface code, in this case the 913 code, can be drawn as follows. So now you know what this diagram means, right? Maybe you don't, but if you think about it, right? So remember the parity check matrix or the stabilizer generators, right? They're specified by the drawing. So in this case, we have one stabilizer generator, which is Z1, Z2, Z4, Z5, right? So if we have our giant matrix of 9 qubits, we have one stabilizer in there which touches 1, 2, 4, and 5 with Z type stabilizer. And these weird circles, they're just kind of chopped off squares that only stabilize 2 qubits. So this would be X6, X9. Clear so far? Check for yourself that you should now be able to write down this like generator matrix, stabilizer generators. Yeah, no question?
So write down the matrix, we would have a couple of four entries for rows, and then the other would have like 2.
Yeah, if we write down a matrix, so there will be of weight 4 poly strings, except for a couple which are weight 2. Yeah. Okay. So another important factor of these codes is what are the logical operations, and one is x4, x5, x6. So that's this horizontal line here. If we put x on these qubits, then we can check that they commute with all the stabilizers as we need, right? Because we have a Z stabilizer on this yellow square. So X anti-commutes with Z4, but X5 also anti-commutes with Z5, so they cancel out, right? Similarly and then if we look at an X-type stabilizer, X commutes with X, so that's easy. And similarly, we have a logical Z operation, which goes from top to bottom. So we have Z2, Z5, Z8, and it commutes with all the stabilizers. So you should check that this works. And then ask yourself, are there other logical operators in this stabilizer? And the answer is yes. And one way to find out is by taking a logical operation and multiplying it with some stabilizer. You'll get another logical operation. Okay, so one very nice property of the surface code is that we can scale it, so we can achieve any arbitrary code distance. And ask yourself, what is nk and d here? Maybe d is harder to compute, but you saw here the example, right? It's similar. And one nice thing to note is that surface codes have a high error correction threshold of about 1%. Let me get to you in a second. So that means that if we have an error rate of 10 to the minus 2, right, then we can scale our code distance arbitrarily and suppress that error to any epsilon. All right, you had a question? Yeah, so there are some qubits that are unchanged by the logical operation. And I guess the reason is that the logical information is encoded in some kind of global superposition. So doing local operations might switch you from one code word to the other. And if it helps your own understanding, you can now write down for yourself the logical 0 state and the logical 1 state explicitly, and then apply these logical operations to them, and you will see that it will switch from logical 0 to logical 1. You might need to no, okay, yeah, it should be clear if you do that exercise. Yeah. The number of physical qubits, yeah. Yeah, so so the question is, why do we care about this? We already have a 713 code, and that's smaller. I guess one factor is that the threshold, it comes from scaling our code distance, right? And the Hamming code might not have a clear path, or the Steam code might not have a clear path to scaling to arbitrary code distance D. So it doesn't have a threshold. Whereas for the surface code, if I have independent errors occurring with probability less than 1%, and you tell me I want a machine that has 10 to the minus 7 error rate, then I'll tell you, okay, pick a code distance of 30 and encode your logical information in these huge surface code patches, and you'll have 10 to the minus 7 error. That's an important factor these days is how these codes scale. And in particular, these new LDPC codes, they have a better encoding range, which is basically saying how many logical qubits can I encode per physical qubit when I scale it up. Right? For the surface code, this is kind of poor because we have order 1 over d squared logical qubits when we scale d per physical qubit. And I added also ancilla measurements. Whereas for LDPC codes, this rate can be can approach 1. But then you lose the nice properties of this like 2D layout. So yeah, it's a push and pull. Let me see if I can finish up with something. Okay. Yeah. You can do 2-qubit operations. You can do CNOTs. I'm not gonna go through this. Okay. So maybe one nice thing to wrap up with, or if I have more time, then maybe we'll go back. But if we have an error, right? We have an error occurring on qubit 5, which is in this case a bit flip error. Then this X error will, if you recall, flip the phase of our two stabilizers, right? This is Z1, Z2, Z4, Z5 stabilizer anti-commutes with the X bit flip, X5. And similarly, this stabilizer will anti-commute. So when we feed the information that this stabilizer and this stabilizer have flipped to our classical computer, the decoder, then it will say, oh, the most likely thing that happened is that an X error occurred on qubit 5, so you should correct that, something like that, right? And similarly, even though we have a code distance of only 3, if 2 particular errors occur on, in a particular configuration, we could still correct it. So say if we have Z4, Z5 occurring on qubits 4 and 5, then 2 syndromes will get flipped. This left one, this blue one, and this right one. But the middle one will get flipped twice, so it's sort of off. Now your decoder might guess, oh, okay, it probably Z4, Z5 got a phase flip. However, it could also guess that Z1, Z2 got phase flipped, right? But actually, either of these guesses is correct. So maybe a question for you is, why would applying Z1, Z2 just as well correct errors as applying Z4, Z5? I'll give you a second. And the answer is these two operations are equivalent up to multiplying it with the stabilizer, right? So if we take Z1, Z2 and we multiply it with Z1, Z2, Z4, Z5, which is a stabilizer, we get Z4, Z5. So these two operations do the same thing in the code space. So how long do I have left? Sorry. 10 minutes. Okay. Wow. Nice. Any questions about decoding before I jump back and try to fill? How do you find the logical X and Z? Um, I guess one way is to look at the code words, and oh, maybe a better one is to look at the stabilizers and find polystrings that commute with all of them. Those are the logical operations, right? And they operate on the logical subspace. Yeah. Other questions? I want to connect it with something you are, maybe familiar with. And so maybe a good topic is, how do we actually compute something with these surface codes? So we've seen how to do Z and X, but that's not that interesting, right? And we can measure in the Z and X basis by just performing physical X and Z measurements on each physical qubit. Then we can compute sort of the Z string or the X string from those measurements. But if we want to compute with more than one qubit, then we need to tile or put our surface code patches on an architecture. So one way to do that is by placing them, in the following manner, and sort of tiling this in the plane with arbitrary many copies. And note that one of them is sort of the mirrored copy of the other one. This will be very convenient because that will allow us to do what is known as lattice surgery. And maybe this is the most advanced topic I will talk about today, so no worries if you don't understand. But if you have your logical Z operator and your Z1 and logical Z operator Z2 on these two patches, and we measure this patch in the middle between our two surface codes, then if we multiply the stabilizer, the measurement result of this Z patch, this Z patch, this Z patch, which is now 4 qubits, right, in the middle, it's a big square, this one and this one, then what you have computed, right, the product of these measurements is the product of Z1, Z2. Okay, so by measuring these stabilizers, we have now computed Z1 times Z2. So this is a joint ZZ measurement. You might get a, depending on the measurement result, you might get a plus or minus one, but this is correctable. So that's one way to interact two surface codes. And similarly, I'll get to you in a second. Similarly, we can do a joint XX measurement by doing a similar procedure, but in the vertical direction. Okay, so what's your question? Yeah, so which ones are I measuring? It's the ones with the blue dot. Those are the stabilizers that I'm measuring. 2 tops and 2 bottoms. I see there are 5 of them here. Actually, there's a 6th one here, which I forgot to draw. Yeah. So, sorry, can you repeat the question?
So to get your simultaneous
Yeah. So you need to do 6 measurements to get this joint Z1, Z2 measurement. By multiplying the results of these stabilizer measurement outcomes, that result gives you the joint Z1, Z2 measurement. So the product of those stabilizers is Z1 times Z2. And this is very convenient. I'm going to skip this. You can do multi-qubit measurements. This is XXX, but it's a little. So now we can sort of abstract this picture away and say, okay, well, we can do ZZ measurements. This is a figure from a different paper of mine, where you can do it in the vertical direction. The picture I draw before, it was in the horizontal direction, but it doesn't really matter. You can do XX measurements in the horizontal direction. You can do poly Z, poly X rotations. These things construct Bell pair measurement, Bell pair state preparation, etc. So then we can start building more and more complicated logical constructs. So for example, a Bell pair measure, Bell state preparation is basically just preparing 0, 0, right? It's a Z basis, or is it? And then doing an XX measurement and some poly correction. And this gives you, 0, 0 plus 1. And similarly, we can do a C0 by initializing an ancilla in plus, and then we do a ZZ. So that's one ZZ lattice surgery, right? We do a merge. And then once we're done with that, we do an XX. And we measure out the ancilla qubit and teleport in the corrections, and we get a C0 operation. So now you know how to do one gate that out of the gates you need to generate the Clifford group. The remaining ones are H and S, and both of them are not as simple. But suffice it to say that they are doable efficiently. And then you can implement the entire Clifford group. And another topic I haven't talked about is how to add, say, Clifford plus T, right? So where does this T gate come from? This is, could be an entire talk by itself. Okay, so let me conclude. So we have learned about classical linear codes, quantum stabilizer codes, which come from the stabilizer generator matrix. Then at the end, we saw surface codes, which have as a unique property that they're represented in some geometry, right? So in this case, it was 2D. And finally, I showed you an example of how to decode errors on the surface code because they anti-commute with particular stabilizers. But there's a lot more in quantum error correction. For example, I haven't talked at all about how to achieve fault tolerance. Fault tolerance tells you, oh, if I have an error occurring in one of my codes, it's not going to propagate everywhere. Right? One error will just be one error or within a particular code block. LDPC codes are a hot topic. Decoding algorithms, which was this black box that I didn't talk about taking your syndrome measurements. How do we compile our algorithms to an error correcting architecture, right? So if you have arbitrary algorithm, how do you place it onto your surface code architecture? And finally, how do we achieve universal computation, right? In particular, this T gate. It's something called magic state distillation. So there's one cool Google group that was started by Austin Feiler. It's called the TQEC Design Automation Group. He gave many lectures at a very basic level. So if you want to learn more, I'd recommend checking out those lectures. And they're trying to develop tools for compiling automatically to error correcting architectures. And they have a huge Google Drive full of recordings of previous seminars. So, thank you for listening to my talk. And this is a complicated picture of what people are working with these days. They're literally working in this SketchUp program, right? That's a Google program to make 3D models to compact or place their circuit in a 3D volume, time-space volume. And people have been making great strides in improving this. So it's a very interesting field of ongoing research. And I hope you learned something today. Thank you.
Okay, folks, we got time for a few more questions. Then we'll take a break, and Eddie, I'm sure you'll be happy to take some more questions during the break as well, but
Yeah.
maybe we can use this time now.
Yeah. Oh, you mean the further topics?
Yeah, these topics.
I see. Yeah, I'm not in the Slack, so I don't know. Oh, okay. Yeah, I could look into that. I don't know if I have good references for all of them, but I could try to think of something. Yeah.
The example after the circuit, not pocket surgery.
Yeah.
Could you explain the current token? How do you apply?
After lattice surgery. So this example, or CNOT? Right. So if we have one data qubit and another data qubit, and they're sort of diagonally adjacent, we can initialize an ancilla qubit between them. So to the right of one and above the other in the plus state. We can do this easily. And then we do our ZZ lattice surgery, right? Our joint ZZ measurement through lattice surgery by merging these two patches. And then similarly, we do the same vertically. That'll give us an XX measurement after that. And just by, going through the math, you'll see that this actually has implemented a CNOT operation if you apply the right poly corrections.
So just to visualize, we have this arrow.
So the measurement outcomes are A, B, and C. They're bits. And then the poly corrections are given by this formula, C, XOR A, and B. Okay, any further questions? Yeah, thank you. So
Okay,
much
everybody.
for all
Let's
the questions. It's been great.
let's thank our speaker one last time.
Thank you.